Greatest common divisors, least common multiples, and we are going to take a look today at the least common multiples part of this. What you will notice as we work is a lot of our strategies for finding greatest common factors can actually be used to find greatest or least common multiples as well. And so that's kind of cool because they work in both fashions. They work a little bit differently, so you have to be a little bit careful about which one you're trying to use and for which purpose, but they're similar. So let's take a look then at a definition. A least common multiple. A least common multiple is the least non-zero whole number that is a multiple of all whole numbers in your set. So if you'll remember, when we started in the last class period with greatest common divisors, I talked about the fact that the word greatest did not mean that it was large, right? It's still a divisor, and a divisor is a number that's smaller, or at least no bigger, than the number we already started with. The same thing's true for least common multiples. Least does not mean it's small. It's small among the things that are already bigger than what we started with. So if you think about making our list of multiples, like back when you were in third grade or whatever, and you learned your multiplication tables, and there are some different curriculums where you memorize lists. That's one way of doing it. That's the way we started when I was in third grade, I remember. And so we memorized a list of multiples of 3. 3, 6, 9, 12, 15, so forth. So those numbers are all bigger than 3, right? They start with 3 and they go up from there. And the same thing's true for all lists of multiples. So you're already starting with something that's at least as big as or bigger than what you already had, and it's just going to be the smallest one of those things. So our first strategy is going to be called the number line method or colored rods. This method doesn't look like the ones we've already done. This is something new. It's a very concrete method. Colored rods are actually something that can be purchased. You could certainly make pieces of paper to do them yourself like this. But they actually exist in the manipulatives world. If you go and you looked up online colored rods, you'll see things that you can purchase that are called colored rods. What they do is that they show multiples of all numbers on a number line in intervals of each value. We're going to do it on a number line. And you find the first value at which the intervals coincide. Okay? So what does it look like in concrete form? Like if you actually buy these manipulatives? Well, it looks like having blocks that are like red, and all the red blocks are the same length. And you have blocks that are blue, and all the blue blocks that are the same length, but the blues and the reds are not the same length. Everybody with me so far? Okay? And there's lots of colors. It's not just 2 colors, but let's just focus on 2 colors at once. And the idea is that you put the red blocks end to end to end in a line, right, like on a number line, and you put the blue blocks end to end to end on a line. And what you want to do is you want your red line to be the same length as your blue line, and the place where they match, that's where the multiples match. Okay, you're trying to get the lengths to match up. And we're going to do this from a number line perspective. Because I can draw that on the screen, but I'll do it with colors so that you can see how it would look from that version too. So our question is actually asking us to find the LCM of 6 and 15 using colored rods or number line method. So here's the way that actually looks. We're going to draw a number line. And I'm going to do it from the colored rods perspective first, and then I'll show you what it looks like if you avoid the colored rods altogether and just think about the number line. So if we're doing least common multiples of 6, first we're starting at 0, 0, and then the first length that we hit is 6, and our colored rod, we'll use the red and the blue that I just mentioned before, and we'll use red for this one, has a length of 6. No, I can't get it to work. Oh yeah, there we go. All right, so what we would really do, right, in real world from colored rods is we would put these reds in order, end to end. And let's put 4 of them there, okay? And then we're going to also have rods that have length of 15. So our rods of length 15 are going to be in blue. That's fairly close in terms of measurement for the other one. And then, whoops, they're end to end, and you can see that I didn't put enough red pieces for that to work, right? And I don't have a convincing argument, but this should be matching up end to end there. So just pretend, because my drawing was certainly not perfect. It should be end to end and match up at that point. I think, yeah, it does. Okay. And so the question would be is when they match up, right, in a concrete sense, what value did we end up them matching up at? And what is it? 30. It's 30, right? So this was 15 long. And this is another 15 long. So at this point where I hit at the end, I'm at 30 on a number line, okay? And I could do the same thing with my 6s. All of these are 6 long, so this point right here would be 12, and this point right here would have been 18, and then this point would have been 24, and then I would have hit 30 as well. Okay, so that's the colored rod, what it would look like. If we were doing the number line and we didn't want to worry about the rods themselves and we just wanted to think about the number line instead, what we can do is we can make sort of jumps, if you will, of those particular lengths. So this is a jump of 6, and I'm jumping another 6, and I jump another 6, and I jump another 6. And in theory, you would jump indefinitely, like we keep jumping forever, quote unquote. But at some point, they're going to match up. So this would be my jumps of 6, and then I would have equivalently, and I'll just change colors just so that we can see them separately, jumps of 15. So there's a jump here to 15. And then my next jump of 15 would have me ending up at 30. So what this is telling me from either one of these pictures is that my least common multiple is the location where both of them land at the same time, which is 15. Not 15, sorry, I meant to write 30, which is 30. That would be the least common multiple of 15 and 6. Okay, so that's a visual perspective of LCMs. Another method is called intersection of sets, and we've seen this method before. It's done a little bit differently for LCMs than it was for GCFs. So this intersection of sets method says to list all, which is not really true. You can't do all, so we'll put some quotes around that. So we'll list all multiples of each value. It might be better to say list a bunch. And then to find the least value that the lists have in common. And of course, the in common comes from the fact that it's an intersection. Intersections are what things have in common. Okay, so this method is very graphically appealing, very visual, right? This method is very number-based, right? This idea of quantitative. So we've got numbers involved. So example number 6, we're going to find the LCM. This time we're going to do the list of 12s and 15. So what we're going to do is we're going to write down one of our numbers, and we're going to do just like we would have in elementary school when we were trying to learn our multiples of whatever, is we're just going to write a bunch of them out. So for instance, we would start with 12, and then we would have 24. So somebody list me a few of the next of them. What's after 24? 36. Okay. And?
48. 60.
Let's get me a couple more.
72.
84. Okay, fabulous. And we'll stop. And in theory, if I stop here, I may not really be there yet. I may have to go back to this list in a little while and say, oh, I needed to do some more. But you don't want to go so far. I mean, like this goes on forever, right? This is an indefinite process. So I don't want to try and sort of list them all. That's not possible. So at some point I have to stop and try the other list and see what happens. So we'll list several in the 15s list. So I start with 15 and then I have 30. So what's next? 45. 60. Now, in theory, I can stop right here, but if you don't see it, let's write just a couple more out. What's after 60? 75, and then 90. And of course, as we've said, these lists continue, ... But what we're wanting is we're wanting the first number that's the same in the lists. And that number is 60 on this one, 60. So the LCM is 60. Now, it's perfectly reasonable on this problem to just write LCM equals 60. Let me also introduce you to another notation that you'll see used sometimes. Sometimes when it wants to clarify the LCM of what, it'll put the numbers in parentheses. So the LCM of 15 and 12, like this, is equal to 60. Just clarifying which two numbers it's finding the LCM of. We're going to see this notation in a little while, so I might as well show it to you here now. Okay? Doesn't mean I'm doing any multiplication or that this is an ordered pair. None of that's present. It's just clarifying LCM of what? LCM of 15 and 12. Okay? All right, the next method, it's another one that we have seen before, prime factorization. So most of these steps are similar, but not quite the same as our other prime factorization steps. Construct the prime factorization of each number. That step's the same. Number 2, choose all prime factors in each factorization. That one's slightly different. We'll talk about why in a minute. Number 3, list each prime with the largest exponent in any factorization. Also slightly different. And then step 4, finding the product of the values. That step's the same. So let's go through this and I'll show you what's happening differently as we do an example. What I want you to see in this example is that I could actually compare more than two numbers, right? I could look at 3 sets of numbers or 4. I could use, however many. So we're going to do an example that has 3 numbers here. So prime factorization, I'm going to still do that division algorithm that I showed you guys last time. So smallest prime number that divides 90. 2, which gives me 45. Next smallest prime number. Smaller. 3, which gives me 15. And then 3, which gives me 5. So the prime factorization of 90 is 2 times 3 squared times 5. Is everybody good with that one? Great. Next one's 50. Starting with 2 to give me 25. And then what? 5 and 5. So that one's done. So this one, its prime factorization is 2 times 5 squared. And then our last one is 20. So that's 2, gives me 10. And then what? 2, and it gives me 5. So I have 2 squared times 5. Okay, really good. Okay, didn't do anything new. That's all just the same stuff we've done. What is different about step 2 is that it says we're going to list all prime factors. When we did the GCD, or the GCF, whatever you want to call it, we listed only the prime factors they had in common. With this method, I need to list all the factors, the bases, all the bases. So for example, there's a base of 2. There's a base of 3. It's not common to all of them, but it is a base somewhere along the way. And there's a base of 5. And if I look at the other lists, they don't give us anything else new. I already have the 2s and the 5s listed, right? So all of my bases that are prime numbers, right, all those bases are included, 2, 3, and 5. That's different. The second one where there's a difference is step number 3. It says list each prime number with the largest exponent. When I did GCFs, I did the smallest exponent they had, right? So if you're taking a look, what is the biggest exponent you see on any prime factorization for the number 2? 2. What is the biggest exponent you see on any factorization including the number 3?
2.
A 2, power of 2. And what is the biggest power on any of the 5s?
2.
It happens to be a 2. That's not always going to be the case, okay? They're just whatever they are. Just like with the other one, though, we're going to multiply out what we have here. So this is my LCM in factored form. Now I need to multiply it out. So I need to know what is 2 squared times 3 squared times 5 squared. Somebody grab a calculator if you wish. Use your head if you wish. I don't care how you do it, mentally or whatever. What is 2 squared times 3 squared times 5 squared? What is it?
900.
900. That sounds right. 900. 900. Okay. bigger than what we started with. That's true, right? I mean, the numbers we started with were considerably smaller. If you were to look back and you were to make a list of like multiples of each one of the numbers, this number would be included in all three lists. Some of them are really obvious, right? Like, is 900 a multiple of 90? Well, of course it is. Like, you see that one very, very quickly. You might have to work a little harder to see why 900 is a multiple of maybe 20. It's just not as easy to see. Okay, but it is. It's a multiple of all of our three numbers, and it is the first multiple that they all have in common. All right, I think, yep, the next one is division by primes. Now, we've done this one before as well. So division by primes, much the same, but there will be a couple differences. So you write the numbers in a row. You divide each of the numbers by a common prime factor, still the same. Step 3 says to divide all quotients by a common prime factor, and then there's this weird note. It says, note, any factor that divides at least two of the numbers can be used to divide the number not divisible, used to divide, and the number not visible simply relisted. So I'll show you what that means. And then we repeat. We repeat until there's no more prime factors, or no more common factors, excuse me. And then the LCM is the product of the primes, and it shouldn't even say necessarily primes, because we might end up with something that's not prime at the end. But it's the product of all primes and remaining factors, so let's include that in. From step 4. And my example shows this, so you'll see it. Okay, again, I chose to do one that had three numbers that we're going to compare, okay? So our numbers are 90, 100, and 20. So slightly different than the last example, but similar. 90, 100, 20. We write them all on the same line. And again, division by prime. So what I want to do is I want to look at them and say, what prime number divides all of them? 10's not prime, but we'll do 2. Yeah, we'll get to the 10 eventually because we'll do a 2 and we'll do a 5. But yeah, 2. So this divides out to be 45. That gives me 50, and this one gives me 10, right? Yeah. Okay, so what about 2? Does a 2 work again? No, it doesn't. But 5 does. 5 divides all of them, so we can do 5. That would be 9. And 10, right? And 2, correct? Okay, now if I have to compare 9, 10, and 2 all together, there's no number that divides all of them, right? But we have this weird caveat over here back in step number 3 that says, note, if it divides at least 2 of them, we're going to keep going. So let me show you what that looks like. Are any of those 2 numbers divisible by the same thing?
2.
Yeah. 2 will divide the 2 and the 10 at the end, right? So here's what this looks like. We write down the 2 as a divisor. The 2 divides the 10 and the 2 divides the 2. And then the 9 just gets relisted. I know it didn't divide it. I get that. And it's okay. At this point, 9, 5, and 1, do any of them have the same factor that can be divided by? No. I mean 1, but nothing else besides 1, right? Okay. So 9's not a prime. Agreed? It's not. But all the primes that divided are over here. And all the remainders that I referenced when I wrote in my little, add in at the very end, they are down here. These are all the remainder pieces that didn't completely divide out. Technically, the 1 divided we were at 1, but the rest of them are still values. Everything I highlighted in orange and green, if you multiply them together, that's the LCM. So my LCM is actually the product of all of these. So the LCM is 2 times 5 times 2 times 9 times 5 times 1. Not in prime factored form, that's okay, but it's all of those values multiplied. And if we multiply all those values, what will we get on this one? It ends up being 900 as well, just like the last one was. Just slightly different values, but still the least common multiple is 900. There's this very interesting formula that pops up. and it shows how the GCF and the LCM are related. Hopefully you've felt like there's something going on here that must relate these because we're using the same methods but just changing a few details. There's got to be some relationship, right? And there is. And the relationship looks like this. For any two, and specifically it does say 2, so this doesn't apply to my last 2 examples that had 3 numbers, okay? For any 2 non-zero whole numbers, A and B, the greatest common divisor of A and B times the least common multiple of A and B is A times B. Let me just do a real quick, easy example so you can see it work. Will that be good? Okay, let's do the LCM GCD, and we'll do the values. A is 4 and B is 6, because we can find the values really quick. All right, so given 4 and 6, can you guys tell me what the GCD of these 2 numbers is? 2. 2 is the biggest number that divides 4 and 6. Everybody good with that? Yeah, it's 2. Anybody know what the LCM is? It's 12. Right? If I wrote out a list, which would be small enough to do on this case, 4, 8, 12, and then 6 would go 6, 12. So 12 is the LCM. So take a look. If I multiply the greatest common divisor, which is 2, times the least common multiple, which is 12, do I in fact get 6 times 4? I do, because 6 times 4 is 24. And it works no matter how complicated or messy. This is just a very simple, small one that we can see it work for. Okay? So our next example is going to rely on an earlier example we did. In fact, it's the last example from last time, the Euclidean algebra one. So if you'll flip back in your notes to what you did, it says we're going to find the LCM of 72 and 126 using the GCD-LCM formula and the results from example 4. So back in example 4, we found the greatest common divisor of 72 and 126. And what was it back on example number 4? Yep, it was 18. So we did this sort of mysterious Euclidean algebra a little bit, and we found out that the GCD was 18 for these 2 values. So the cool thing is if I know one of the values, I can use it with this formula to find the other one. Because this formula says that if I multiply the greatest common divisor times the least common multiple, I get the product of A and B. Well, my A and B here are my 72 and 126 in whichever order you'd like. And I know from example 4 that my GCD was 18. So I should be able to find my LCM because it's the only piece of information I don't know. So grab a calculator for me. What is 72 times 126? I don't have this written down, so somebody's going to have to tell me.
9,072.
Like this? Okay. And then what would we do to find the LCM? Yeah, I would divide by 18. So the LCM would be 9,072 divided by 18. And what does that give you? 504. It's actually really nice because if you're asked to find the GCD and the LCM of the same 2 numbers, you almost get one for free. I mean, like, this isn't actually for free. There's a little bit of work here, but way less work than any of the other methods I showed you. Wouldn't you agree? Really is a lot less work than division by primes or prime factorization or whatever else. All right, so let's give a couple of examples. I want to show you where these types of problems show up in a real context situation, real context. Because you're going to see questions asked of you, and they're going to look a lot like the examples on the next page. And they're not going to say, find the GCD of these numbers. They're just going to ask you a question, and you need to be able to looking at it know, this problem is an example of a GCD problem. So I'll use one of my GCD methods to find the answer to this problem. Okay? I'll also tell you that occasionally I have asked in the past on a test the same kind of thing. Or I've asked reversed. I've said, create a greatest common divisor question. Create a least common multiple question. And no, you may not say in your question, use the GCD to find the result. Your context has to force that to be what you need to do. Okay? So let's take a look at a couple of examples. 2 bike riders ride around a circular path. The first rider completes 1 round in 12 minutes. The second completes 1 round in 15 minutes. If they both start at the same place, at the same time, and going in the same direction, all those pieces are necessary. If they start in different spots, if they go different directions, or the next part says they continue the consistent pace, if they slow down or speed up, everything's off limits. I mean, nothing else applies. Those details are important. So they start the same place, the same time, going the same direction, and continue at a consistent pace. After how many minutes will they start and meet up again? So picture what's happening. The first person goes around in 12 minutes, and then they go around again in another 12 minutes, which means they've been riding for 24 minutes. And they go around again in another 12 minutes, which now means they've been riding for 36 minutes. Is this a GCD problem or an LCM problem? It's an LCM. They're repeating the same loop over and over and over again. And if you notice, the numbers you're giving me are exactly that. They're multiples, the multiples of 12. Okay, everybody good with that? First thing you have to decide in these problems is which kind of problem am I looking at, a GCD or an LCM? This is an LCM problem. So what they're really asking you for is what's the LCM of 12 and 15? And then you get to pick which method you want to use to solve it. We had a bunch of methods. I showed them to you today, right? Division by primes, prime factorization, intersection of lists, or intersection method or the listing method. We had the colored rods method. Which method do you want to use? Somebody has to pick. Lists. These are small numbers, so lists work actually really well. If the numbers get bigger, lists become more cumbersome, but these work really nice. So if I do lists, I need to write out multiples of 12. So 12, what's next? We've done this list before. 24, 36, 48, 60, I'll go 72 and then I'll stop. And then 15. And honestly, you can stop there. How come? Because I finally got one to match. So I'm done. They matched at 60. So the answer then to the question, because you still got to answer the question, right, is what? 60 minutes. They will meet again at the starting spot in 60 minutes. Now, along the way, somebody may pass somebody else. That's a possibility in this particular scenario. That wouldn't be the answer to the question, though, right? Because they need to be passing one another at the starting spot. That's the way that the question was constructed. That's why I know it's going to be a multiple of those numbers instead. Make sense? There's another really good pop culture example, although at this point it's probably dating my age, and maybe you guys haven't seen the movie. But has anybody seen the movie of Father of the Bride, the very first one? Okay. So, Steve Martin, he's the father, and he's in the grocery store. And he is super, super stressed out. And does anybody remember the scene that he makes in the grocery store? It involves hot dogs and hot dog buns. And he gets really frustrated because the hot dogs are sold in multiples of 10, I think, in his scenario. But the hot dog buns are sold in packages of 8. Right? This is a problem. He wants to have the same number of hot dogs and hot dog buns. It's a least common multiples problem. He just needs to figure out how many packages of buns and how many packages of hot dogs, right? So that they have the same number of them. But he stresses himself out because they're in different packaging amounts. And if you don't think that marketing people do that on purpose, you're probably a little naive. They definitely do that on purpose, right? They do. Okay, let's do another example. Dr. Hands makes cupcakes for her students. She makes 20 chocolate cupcakes and 24 vanilla. She wants to display them on plates with the same number of cupcakes on each plate, but only one type of cupcake on each plate. What is the greatest number of cupcakes she can put on each plate? Yeah, this is a divisor problem. We're dividing the cupcakes up among plates. Does everybody see that okay? Okay, so let's talk about the structure of why it actually works for this to actually be that kind of a problem. Number one, the chocolate and the vanilla are not intermixed. If you intermix the chocolate and vanilla, then you lose the fact that there is the number 20 and the number 24, and all of a sudden you just have 44 cupcakes to divide up. And you might end up with a different solution, okay? So you can't mix the cupcakes up. That wouldn't work for this to actually be a GCD problem. You also have to have this phrase in here where it says something about the greatest number on each plate, and the phrase that says all the plates have to have the same number, right? Because 20 and 24, I mean, I could put 20 in groups of 5, and I'd be cool with that. But I can't put 24 in groups of 5 and evenly display all my cupcakes, right? So there's a lot of phrasing in here that forces this to actually be a GCD problem. You don't just get it for free by making cupcakes and saying put them on plates. There's a lot of pieces in here that make that happen. But it is a GCD problem. Same number of cupcakes on each plate, the most number of cupcakes on each plate, no cupcakes left over. I don't even know if it says then there should. It should say no cupcakes left over. And then, of course, not intermixing them. So this is a GCD problem. I'm looking for the GCD of 20 and 24. And we got a lot of methods. We didn't do them today. We did them on Friday last week. But one of those methods is division by primes. One is prime factorization. One's the Euclidean algorithm. One is the listing in terms of sets. All those are possible. Let's do prime factorization really quickly, just because it is small enough that it works out pretty fast. So if I divide 20 by 2, I get 10. Again, I get by 2, I get 5. So this is 2 squared times 5. 24 divides by 2 nicely as well. I get 12. By 2 again, I get 6. One more time by 2, I get 3. So this is 2 cubed times 3. So if I were doing LCM, which was what we've just talked about, we would list all of the bases. I'd list a 2, I'd list a 3, and I'd list a 5. But if I'm doing GCD, I only list the bases they have in common. So what are the bases that they have in common? Just the number 2. And then if I were doing LCMs, I'd list the highest exponent. But if I'm doing GCDs, I list the lowest exponent, which here is a 2. That's a terrible 2. Let's try again, 2. And that's it. And then I multiply it out. So this would end up being the number 4, right? So what is the greatest number of cupcakes she can put on each plate? 4 cupcakes, right? So if I put 4 cupcakes of chocolate on each plate, I'll have 5 plates of chocolate. Is that the right one? Yeah. And if I put 4 cupcakes on each plate, I'll have 6 plates of vanilla. But there's still 4 cupcakes on each plate. Does that make sense? All right.